Here we have the examples and U-triads for sections 7.2 and 7.3, which deal with simplifying radical expressions, that's section 7.2, and operations on radicals, which is section 7.3. So the first few here are from 7.2, and they deal with simplifying radicals using those two properties, right? These two properties are essentially what you're using to simplify all these radical expressions. Now, the top one is the one that's going to be more frequently used because there's a lot less division problems than there are multiplication problems. Okay? And the thing that you're going to have to realize is, in some instances, you're going to be using these properties from left to right, and in other cases, you're going to be using them from right to left. All right? So I'll go through the examples, and then you can try the U-triads. All right? So example 1 is square root of 2 times the square root of 50. All right? So that actually looks like the right-hand side of this top property, right? Which says the square root of a times the square root of b. So a is like 2, and b is like and b is like 50. So what the property tells us, looking from right to left, is that this can be written as the single square root of 2 times 50, right? And 2 times 50, of course, is just 100. So this thing is really just the square root of 100, which of course is 10. Okay? And remember, when you see that radical sign, right, without a negative sign in front of it, it means that you're taking the principal, which is the positive square root of the number. Right? So that's positive 10 and not negative 10. Right? And not plus or minus 10. Right? Right? So when you see the radical sign, you take the principal or the positive square root of the number. So the square root of 100 is 10. All right? And then 2 is really the same property, except now you're using it from left to right, because the thing that you're starting with is a single square root of something times something. All right? So what that property tells us now from left to right is that we can break this radical up and write it as the cube root of the first thing, which is negative 8, times the cube root of the second thing, b, which is y to the 6th. Right? And now, both of these are perfect cubes, so we can take the individual cube roots of these. So the cube root of negative 8 would be negative 2, and the cube root of y to the 6th, right? We do 6 over 3, divide the power by the root, and we would get y squared. So that would just be negative 2 y squared, right? So both of those were pretty straightforward because they use the property either from right to left or from left to right, and then you ended up with a perfect square or a perfect cube that just, simplified nicely. So there were no radicals in your simplified answer. Now, example 3, there's actually 2 different ways to do example 3. You can try to simplify the 2 radicals individually and then combine them later. But what I usually find is the easier thing to do with these problems is to first combine them into a single radical, right? So this is kind of like, again, the top property. This is like the square root of a times the square root of b. So the square root of a times the square root of b is really the same as the square root of a times b, right? So in this case, a is 3x and b is 12x. So that's the square root of 3x times 12x, which is just the square root of 36x squared, right? And as is the case in the above ones, these are both perfect, right? So now I use the property actually in one direction, right? I wrote the square root of a times the square root of b as the square root of a times b, and now I'm going to break it back apart again, right? And I'm going to write this, which is the square root of a times b, as the square root of a times the square root of b. So it's the square root of 36 times the square root of x squared, and of course the square root of 36 is just 6, and the square root of x squared technically would be the absolute value of x, but what we would probably see here is we would see a statement at the top that would tell us to assume variables are positive. So then we wouldn't have to worry about the square root of x squared being the absolute value of x, because if it's already positive, we don't need to take the absolute value, right? It's already going to be positive. So we don't have to worry about that. So again, that one actually worked out perfectly, right? There's no radical in the answer, because 36 is a perfect square and x squared is a perfect square. So we just end up with 6x. Okay. Now 4 is the only one out of these first 4 that we did where you're actually going to end up with radicals in the answer. Okay. So what I usually tell people to do with this is, I usually tell them, all right, well, what you're going to do is you're going to break this single radical, right, up into 2 sides, right? You're going to have one side that would be your perfect squares, and then your other side is kind of like the remainder after you take out the perfect squares. What we want to do is we want to take out perfect squares from this expression here. So inside of 20, is there a perfect square? Yeah, there is actually, right? 4, right? I can write 20 as 4 times 5. So the square root of 20 can actually be written as the square root of 4 on my perfect side and the square root of 5 on my remainder side, right? Because 4 times 5 is 20, so that actually works. And then a cubed, right? Is there a perfect square inside of a cubed? Well, sure there is, right? A squared. A squared is a perfect square. So if I take out the square root of a squared, now I'm left with the square root of a on my remainder side. And now b squared already in itself is a perfect square. So I would just leave this on my perfect square side. So I have my perfect square side as the square root of 4 times the square root of a squared times the square root of b squared, and my remainder side is the square root of 5 times the square root of a. So my remainder side is going to just stay the way it is, right? The square root of 5 times the square root of a is just going to be the square root of 5a. But my perfect square side I can simplify, right? Because the square root of 4 would be 2, and the square root of a squared would be a, and the square root of b squared would be b. So this is just going to be 2ab times the square root of 5a, right? So whenever you have problems like that aren't perfect squares in themselves, you want to look for a perfect square that you can divide out of it, basically, right? So in the case of 20, we can look at 20 as 4 times 5, right? A perfect square times a non-perfect square. Now, some people might tell you, well, all right, well, 20 you can write as 10 times 2 also. Yeah, you can, but the problem is neither 10 nor 2 are perfect squares, so you wouldn't want to write it that way, right? You always want to break it down to factors where one of the factors is actually a perfect square, like in this case, 4 times 5.